Today we're going to talk about functional notation, or function notation. In algebra, variables such as x and y are used to represent unknown or changing numbers. When the relationship exists between two variables as a function, we can use this functional notation. And this functional notation takes some getting used to, but with practice, it is really, really valuable. So to represent functions, sometimes we use the symbols f of x and g of x. So for example, y would equal 3x plus 1 would be written as. So let us consider we have two variables, y and we have x in this formula. And this formula is a linear function. But we can write this linear function using functional notation. We can, instead of calling it y, we can call it f of x. We can call it g of x. Now, before I go to h of a, I am going to start talking about this. And what we see is f of x is equal to 3x plus 1. Now, this is kind of difficult to understand. However, this on the left-hand side can be thought of as y. So f of x is really your y. Well, why do we write it in such an elaborate way? Because it definitely helps it. Now, on the right-hand side is basically the rule upon when we input an x, we put x into the rule and we get out a y, or a value of f of x. Now, why is it the weird f of x? F meaning function. X is in the brackets. Because x, whatever variable is in the brackets, this input variable, will have to appear in the rule. So, since if I see f of x, I know a function, f means function, of x means the input of my function is x. So my independent variable is x. So naturally, so far in grade 10, a lot of our independent variable has been x. So we will continue with this. However, we don't always need to have f of x. We might have a function h, and my input is a. So I have this function h, which might be height. H for height. A might be for some other variable, maybe apples. Maybe, just maybe, I have thought of some crazy formula that determines the height of people given the number of apples they eat. Now, this is absolutely ridiculous, I understand, but when I see h of a, I know that on the right-hand side, I have a rule that has a as an input. So this functional notation was first used by a mathematician called Euler in the 1700s. An amazing, amazing mathematician Euler was. The symbol f of x is read as f of x. So that's how that's how you'll hear it. Other teachers said f to x or something like that. I don't understand it. But anyways, this means that the expression that follows the variable contains x as a variable. So this notation is really useful for two reasons. Number one, it simplifies the recording of the values of the function for several values of x. Sure. But more importantly, it allows us to refer to different functions by a name. So if I have one function, I can call it f of x. And if I have to graph a second function, I can call it g of x. And although f and g might be lines, I can tell the whole class, look at f of x. And you will be drawn to, your eyes will be drawn to the function that is known as f of x. Whereas g of x is another one. One thing that I think is missing about a strength of functional notation is that you can choose variables that make sense in the context of a question. We'll see a little bit of that later. We don't always have to deal with x and y's, by the way, right? So the notation is another way of representing the y value of a function. Y is equal to f of x. So when we graph, the y-axis might be, right, when we graph, we have the x-axis and the y-axis. Sometimes we call it the f of x axis. You don't always need to, though. So let's start. We're going to write each equation in functional notation. My variable c, n. So those are my two variables. So if I want to write this in function notation, c of n. Now I know that c is determined by the variable n. How? By taking 20 times n plus 8. So p of n minus 3. And simply because p is determined by the rule where n was an input. Similarly, t of d. And now, actually, y of, yeah, we don't do that, right? We might want to call this f of x is equal to negative x minus 4. Generally speaking, we don't call it y of x. We just don't. It just doesn't look right, or it can be misleading. So there we have it. So here, for example number 2, we're going to write each as an equation in two variables. So when I take a look, I have two variables, and I like to, whenever you see functional notation, here, d of t, I look at it, whatever's in the brackets is actually just silent. So if I was just to write this in two variables, all I would have to do is take away that t. It doesn't really do anything other than pure notation. F of x is equal to negative 6x plus 4. I would just write this as f is equal to negative 6x plus 4, and so on. Now, let me move to example number 3. Now, example number 3 is where we're going to earn our money. And this is we're going to start to see the real strength of functional notation. Just going to get a glimpse. This is your first time with functional notation. But if I look, f of 1. What f of 1 means is that my input is 1. So I'm just going to write my function f of x is equal to negative 5x plus 11. What that means, now if I want to calculate the f of 1, it means that my input for x, I'm now going to write as 1. So I plug in 1 into x. So wherever I see an x in the rule, I just simply write 1. And there we have it. Similarly for b. Now I'm going to write my function in functional notation like this. So here I have the f of negative 3, and I'm just going to plug it wherever I see an x. And what comes down is I get negative 14. How can I interpret this as a point? Great. Remember that this is the x. So this corresponds to x. Now, my value of my function, I've calculated using the rule. The output is my y value. So here, the f of negative 3 is equal to negative 14. That corresponds to my x and y coordinate. So the f of 0 is going to be negative 5 times 0 plus 11 is going to be 11. This corresponds to point 0, 11. So not that it's really important, that it's not the purpose to find out a point, but it should note it's an interesting, whenever you see f of 0, it corresponds to the y-intercept, because that is the x, or whenever x is equal to 0, we'll have a y-intercept.